Hi, I'm Raghav, and this study proposes a method to robustly train deep neural networks in the presence of noisy labels. Broadly speaking, there are two types of label noise, open set and closed set. Closed set noise occurs when your dataset contains samples that are mislabeled, but their true label is within the known label set. On the other hand, open set noise occurs if there are samples in your dataset whose true labels are not in the known label set. For instance, if your dataset consists of images of wolves and dogs, then any image that is mislabeled as wolf but is actually a dog or vice versa belongs to closed set noise, and images that are neither wolves nor dogs belong to open set noise. Traditionally, the study of closed set noise and open set noise has been done in isolation from one another. In other words, all the systematic studies, at least in a controlled setting, that have been presented, evaluated the methods on datasets that were exclusively corrupted with either closed set noise or open set noise. However, it's very easy to argue that both open set and closed set noise are likely to co-occur in real-world datasets. Therefore, in this work, we formulate a novel benchmark evaluation to address the noisy label learning problem that consists of a combination of closed set and open set noise. The state-of-the-art approaches that aim to solve the closed set noise problem focus on methods that identify the samples that were incorrectly annotated and update their labels with semi-supervised learning techniques for the next training iteration. This strategy is not likely to work in the context of open set noise because it assumes that there exists a correct label in the known label set for every training sample, which is not the case. On the other hand, the main approach addressing the open set noise problem targets the identification of noisy samples to reduce their weights in the learning process. Such strategy is very inefficient for closed set problems because the closed set noisy label samples are still very meaningful during the semi-supervised learning stage. Hence, to be robust in the scenarios where both closed set and open set noise samples are present, the learning algorithm must be able to identify the type of label noise affecting each sample and then either update the label if it's closed set noise or reduce its weight if it's open set. One of the most successful methods to identify noisy samples uses something called the small loss trick, which treats a certain number of samples with small loss as clean and thereby filtering the noisy training dataset. However, the trouble is, given that these methods do allow to separate the clean samples from noisy ones, they don't quite distinguish open set samples from closed set samples if they are present at the same time, as shown in the rightmost figure. To deal with this, we propose the use of subjective logic loss, which relies on the theory of evidential reasoning and subjective logic to quantify classification uncertainty, as evident from these figures. The use of this loss function allows a very clear separation of clean, open, and closed set samples. Overall, our proposed method simultaneously trains two networks, NetS, which uses subjective logic loss, and NetD, which uses a semi-supervised learning mechanism. Broadly speaking, the ability of subjective logic loss to estimate classification uncertainty allows NetS to divide the training set into clean, open, and closed set samples. The predicted clean set and closed set samples are then used to train NetD using techniques like mix-match, while the predicted open set samples are discarded for that epoch. Following this, NetD relabels the entire training dataset, including the predicted open set samples, that are then used to train NetS. As NetS iteratively learns from the predicted labels by NetD, it gets better and better at splitting the data into the three sets. This is because the labels from NetD become more and more accurate over the training process, given that it's only really trained on the clean and closed set samples and never on the predicted open set samples. The two networks thus complement each other to produce accurate classification results for the combined closed set and open set noise problem. We tested our method on CIFAR 10, where the open set images were sourced from CIFAR 100 and ImageNet. Our method produced state-of-the-art results on 17 out of the 20 different noise scenarios we tested it on. Furthermore, we show that our method can learn superior feature representations than previous methods, as evident from the clusters in this TSNE plot, where our method has a unique cluster for each of the known labeler class, and another separate cluster for open set samples, which is represented by the brown dots. Unlike the previous methods that have sort of shown to largely overfit open set noise, which is evident from the spread of these brown samples across the entire distribution. The motivation for introducing this problem was to open the dialogue in the research community to investigate the combined open set and closed set noise problem. In this work, we investigated a rather simple kind of label noise, which is symmetric label noise. That is, the process of introducing synthetic noise used a uniform random distribution. In real-life scenarios, however, that is not the case, and moving forward, we aim to explore more challenging noise settings, such as incorporating asymmetric noise and symmetric noise in the proposed combined setup.